Let us consider the situation where we have two parallel plates. They are located at a distance h apart. So the gap between the two plates is h, and one of the plates moves with a velocity with respect to the other. So for generality, we can assume that the top plate moves at a velocity u with respect to the bottom plate. This action is essentially a combination of, not a combination, this is essentially shearing, and this is more common than you think. So if you consider two big journal bearings, so there is a fixed cylinder like this. There's a fixed cylinder like this, and there's another cylinder like this. So the fact that they're eccentrically placed means that when this begins to rotate, there is fluid flow between this small gap. So the fluid otherwise is not flowing, but if you zoom into this location, so if the rotation direction is like this, if you zoom in, you have the top plate like this, you have the bottom plate like this. So the diameters are quite large compared to the gap. So if you zoom in, it will appear that the gap is almost comprised of two parallel plates. Well, the fact that it does have a curvature, it does matter, but for the analysis of this location, it does appear that the top plate is moving at a certain velocity with respect to the bottom plate, which is grounded. So this kind of flow configuration is called as a couette flow. So in in addition to this, the plate being dragged, you can have a pressure driven component as well. That is, additionally, you can have a pressure which drives the flow. So minus del P star del X can also additionally act in combination to U to drive the flow. So what we will be analyzing is a combined pressure driven couette flow. Let us write down the governing equations for this. So once again, the continuity equation or the incompressible condition is this. So once again, we consider fully developed flow so that del u del x is 0, or rather any gradient in x directions are 0, and we consider that the walls are impenetrable. That is, the velocity field cannot exist in this direction. So at the walls, we will have u equal to 0 and v equal to 0. These are consequences of no slip and no penetration boundary condition. So the governing equation in the x direction, and the governing equation in the y direction. So now we will make use of all the assumptions in order to simplify these equations. So apart from being a fully developed flow, we assume that the flow is steady. So if the flow is steady, these terms will vanish. So right away, if it's a fully developed flow, del u del x is 0. So del u del x will be 0, and that implies del v del y will be 0. And if this is true, v equal to constant. I mean, v could be only a function of x, but because it's a fully developed flow, v cannot be a function of x. So v is a constant, and because v equal to 0 at the walls of the domain, at constant it is equal to 0. So v equal to 0 everywhere. So it becomes a unidirectional flow. There is no other component of flow apart from the flow in the x direction. Okay, so it's a unidirectional flow. So now because the flow is steady, this term vanishes, this term vanishes. Because it's a fully developed flow, this term vanishes. Because v is 0 everywhere, this vanishes, this vanishes. Okay, this vanishes and this vanishes. Now because the flow is fully developed, this also vanishes. Because v equal to 0, this vanishes. So finally what we have is from the x momentum equation 0 equal to minus del p del x plus mu del 2u del y2, and from the y momentum equation we have 0 equal to minus del p del y. Once again, I am not writing down the gravity component because that can be written down in terms of the modified pressure P star equal to P plus rho gy. So we can simply make them stars. So P star is the modified pressure. So this implies P is only a function of x. Okay. So this equation can be simplified to minus dp star dx, and because u is only a function of y, because it's a fully developed flow, this becomes d2u dy2. So the Gurney equation is the same as the plane Poiseuille flow, but the key difference will be in the boundary condition. So the boundary condition will be, so if I choose the coordinate system over here, so at y equal to 0, u equal to 0 by no slip, and at y equal to h, u equal to capital U, and this is also by no slip. So the no slip boundary condition implies that the relative velocity of the fluid with respect to the boundary has to be 0. So the relative velocity of the fluid with respect to that particular boundary has to be 0. It means that the absolute velocity of the fluid at the top wall has to be equal to capital U. So this is also a consequence of no slip. So now we have to solve this differential equation subjected to this boundary condition. So let us see. So dp star dx is equal to mu d2u dy2. Now once again, because p is only a function of x, right? So each has to be a constant because this is a function of x only, and whatever is on the right hand side is only a function of y. So each of these things is equal to a constant. As in the previous case, if dp dx is constant, then p will be a linear function of x. Okay, p will vary linearly, so along the channel length p will go down linearly. So if this is x, this is the profile for pressure. So regardless of that, dp dx will be a constant, so we can directly integrate this expression itself without worrying about what this is. We can all keep in mind that this will be a constant. So 1 upon mu dp star dx is equal to d2u dy2. So du dx du dy will be equal to 1 upon mu dp star dx times y plus c1, and u is equal to 1 upon mu dp star dx y square, so 2 goes over here, plus c1y plus c2. So this is the expression for the velocity. Now for the first boundary condition, at y equal to 0, u equal to 0. So 0 is equal to 1 upon 2 mu dp star dx. So y is 0 plus 0 plus c2. So c2 becomes 0. And for this boundary condition, at y equal to h, u equal to capital U. So capital U is equal to 1 upon 2 mu dp star dx h square plus c1 h, because c2 is 0. So c1 is u minus 1 upon 2 mu dp star dx h square, and then you have to divide everything by h. So this h square becomes simply equal to h. So now we can find out the total, we can substitute this constant in the function and find out an expression for the velocity. So it becomes 1 upon 2 mu dp star upon dx y square plus c1y. C1y means this times y, so it is minus 1 upon 2 mu dp star dx hy, and this other term plus u y upon h. So we can simplify this as minus 1 upon 2 mu dp star dx h square. So this will become y upon h, and this will become minus y square upon h square, and this will become plus u y upon h. So finally the velocity, so I can call this velocity as up, that is the velocity because of the pressure driven flow. So u becomes equal to up y upon h minus y upon h squared plus capital U y upon h. So this is the velocity profile. So naturally, when the pressure gradient is 0, then up becomes 0. So the velocity profile simply becomes capital U y upon h. So this solution itself is the couette flow profile. And as you can see, this velocity profile is linear. That is, it is something like this. So the velocity over at this location is capital U. Then it linearly reduces and becomes 0 over here. Now you can go to MATLAB or whatever software you like, and you can plot this for different values of UP. In fact, we can make everything dimensionless by dividing everything by UP. So rather we can divide everything by capital U. So U by capital U, this will be UP upon capital U y bar minus y bar squared plus y bar, where y bar is equal to y upon h, is the dimensionless y coordinate. So this can be written as u bar, this can be written as up bar, this is y bar minus y bar square plus y bar. So up bar is actually up upon capital U, which is the ratio of pressure driven component of the velocity to the couette component of the velocity. So depending on which term is dominant, you will obtain different flow profiles. So if the flow is dominated by UP, that is if UP bar is quite large, then you will tend to see a parabolic profile rather than a linear profile. But if the plane Poisson component, that is UP, is quite less compared to U, capital U, then you will obtain more or less a linear profile. I'll just draw some profiles. I mean, obviously these are not computer generated. So in the absence of any pressure driven flow, this will be the profile. So these are just like schematics. But if there is a pressure driven flow, then on top of this, there could be a flow like this. If the pressure gradient is in the opposite direction, so this is for dp dx negative. That is, it is driving the flow in the positive x direction. If dp dx is positive, then you will obtain something like this. This is dp dx positive. So in the case of combined flow, there is obviously a point in the flow where there is a maximum velocity occurring, or there can be a minimum velocity occurring. Let us find that value out. So du bar dy bar is equal to up bar 1 minus 2 y bar plus 1. So when is this 0? It is 0 when, so let me just rearrange the terms. So in order to find the maximum or the minimum velocity, this has to be equal to 0. So what do we have? 1 upon up bar is equal to 2y bar minus 1. So 1 plus up bar upon up bar upon 2. So this will be the location of the extrema of the velocity. Okay. What is the wall shear stress? The wall shear stress for such a problem can be found out using the expression for the shear stress, which is mu del u del y plus del v del x in general. But because in this case the y component of velocity is 0, this vanishes and this simply reduces to mu du dy, because u is a function of y only. So this is mu upon capital U du bar, because u bar is u upon capital U, upon dy bar times h, because y bar is equal to y upon h. So this is sorry, this u should be on the numerator. So it is mu capital U upon h du bar upon dy bar, and du bar upon dy bar we can simply write down the expression. This is up bar times 1 minus 2y bar plus 1, and we have to evaluate all this at, so tau wall will be at y equal to 0. So at y equal to 0, so we have mu capital U by h up bar, so this is plus 1. At the top wall we will substitute y bar equal to 1, so you get the idea. So using this we find out the expressions for the wall shear stress. In case the up bar component is 0, that is there is no pressure driven component, the wall shear stress, it simply becomes equal to mu u upon h. I mean this becomes 0, so only 1 remains. So this is simply the shear stress for a linear profile. And as you can imagine, if you have a linear profile, the slope is constant throughout the domain, and so this is the shear stress everywhere. This is the value of the shear stress everywhere.